When you look at a game world full of characters, vehicles, and all sorts of items, everything feels solid. Objects tumble, roll, tip over, and collide in ways that look natural. That realism comes from rigid body dynamics, the branch of physics that governs how solid objects move and rotate in 3D space. It's the foundation of every modern physics engine. Up until this point, we've talked about point masses, simple particles that can move, and that's pretty much it. They're great for simulating some objects, but they have limitations. A point mass can't spin, it can't tip over, and it doesn't have a shape. A rigid body, on the other hand, has orientation, angular velocity, and behaves like an actual physical object in response to the forces exerted on it. In this video, we're going to build the rotational core of a real rigid body system. By the end, you'll have a minimal but fully functional physics engine component that can simulate rotation and orientation using quaternions. Before we get started, I'd like to say a big thank you to Ksheshik, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev or by joining the YouTube channel as a member. As I said, point masses are great if you just want to simulate throwing a ball in the air while ignoring its rotation. Just apply the initial force and gravity and let linear kinematics handle the rest. But if the shape of the object is anything other than a sphere, the result is not so good. In the real world, these objects tend to rotate around their center of mass. In theory, the total force is the sum of forces that act on every particle in the object. The result also depends on the way that mass is distributed over the entire object and the distance from each particle to the center of mass. To simplify things quite a bit, we're going to assume that mass is distributed evenly. This means that in terms of the linear movement, we can treat the rigid body as a single point mass. Now, just to clarify things, a rigid body is non-deformable. The distance between the particles is constant, and this is true even when we apply force on the object. Now imagine that there is some virtual wrench which is holding the object by its head. When a force is applied to this wrench, we expect the object to rotate. Our aim is to calculate this rotation. To make things simpler, let's see how this works in 2D. So we have the object lying on a plane and rotating around its center of mass. We can create a two-dimensional coordinate system with the origin placed on the center of mass. We represent the angle of rotation as theta. Velocity in linear kinematics is the change of position over time, so the angular velocity is the change of theta over time. We represent it as omega and write it as a derivative as follows. The angular acceleration is the change of the angular velocity over time. We represent it as alpha and write it as a second derivative as follows. In rotational physics, we usually measure the angles in radians instead of degrees. Remember that the radian is the ratio between the length of the arc and the radius. When the two values are equal, we get 1 radian. We get 2 radians when the length of the arc is twice the radius. How many radians in a complete circle? Well, the circumference of a circle is 2 pi radiuses. If 1 radian is when the length of the arc is 1 radius, then in a complete circle we get 2 pi radians. Since theta is specified in radians, we can write it as the ratio between the length of the arc and the radius. When the object rotates around its center of mass, all the particles it is composed of rotate along with it. For any given point on the object, the tangential velocity is the part of that point's velocity which is perpendicular to the radius at that point. It represents how fast that point is moving due to the object's rotation. Obviously, the tangential velocity of a point which is further away from the center of mass is greater than the velocity of a point closer to the center. This is because for a given theta angle, the further you are from the center, the longer you need to travel to complete the arc corresponding to that angle. The tangential velocity itself is a vector whose direction changes as the point travels around the center. Based on the definition of the radian, the derivative of theta with respect to time is actually the derivative of the ratio between the length of the arc and the radius with respect to time. The reciprocal of the radius is constant, so we can pull it out and get the following. The tangential velocity is defined to be the derivative of the length of the arc with respect to time. Let's call it v. The result is that v equals to the radius times omega. Intuitively, since omega is the same for all points on the object, if the radius of one point is twice the radius of the other, the tangential velocity of the furthest point is twice the tangential velocity of the closer point, and this makes sense. In a similar way, we can calculate the tangential acceleration as follows. The tangential velocity brings us to the next concept, which is torque. Torque is a measure of how much a force causes an object to rotate around an axis. This might make you think that torque is simply a rotational force, but in fact, there is no such thing in physics. Force is always linear, which is why we describe it as a vector. Torque is what force does when it is applied at some distance from an axis. The best example is again the wrench. We can pull or push the wrench. This is force applied along a direction perpendicular to the wrench. Torque is the result of applying force on the wrench. That's the distinction between the two. Intuitively, we all know that we should apply force to the wrench at the end of the handle rather than close to its head. So applying the same force at two locations actually generates different levels of torque. This brings us to the definition of torque as the cross product between the vector from the center of mass to the point where force is applied and the force vector. Based on the definition of the cross product, we can say the torque is a vector which points along the axis of rotation or the opposite of it. This is why torque is sometimes referred to as a pseudo-vector. It represents an axis, not a linear push. The magnitude of the torque vector tells us how strongly the object is being pushed to start rotating or to change its rotation. Torque is usually represented by the Greek letter tau. Since we are currently on a 2D plane, there is only one axis of rotation, the vector which is perpendicular to the plane, or the one which is pointing out of the screen in this case. Therefore, torque is just a scalar number, and we can drop the cross product and write the formula as the radius times the perpendicular component of the force. This is the part of the force applied along a vector perpendicular to the vector from the point to the center of mass. Based on Newton's second law, we know that the tangential acceleration is the tangential part of the force divided by the mass. And we already saw that the tangential acceleration is the radius times the angular acceleration. Therefore, the tangential part of the force is mass times the radius times the angular acceleration. We can now plug this into the formula of torque and get the following. So this is for one point or particle in the rigid body, and to get the total torque, we have to sum up the torques for all particles in the body. This gives us the following equation, and the component in the parentheses is called the moment of inertia, represented as capital I. Notice how similar it is to Newton's second law, which tells us that force causes linear acceleration and mass resists linear acceleration. In the rotational version of this law, We have torque, which causes angular acceleration, and the moment of inertia resisting angular acceleration. Now, actually calculating the moment of inertia for a given rigid body can be quite a hassle, which is why in practical physics, as well as in physics engines for video games, we usually use a pre-calculated table for common shapes. So if the rigid body looks like a cylinder, a sphere, a torus, a box, or etc., we can simply grab the formula from the table. This means that in our physics engine, we will need to let the user specify the shape and its parameters, and internally calculate the moment of inertia when we calculate the effect of a force applied on a rigid body. Okay, so now that we are masters of 2D rotation, let's expand our knowledge to 3D. Basically, each idea is going to get an upgrade from a scalar number to a vector or a matrix. In 2D, the rotation axis is fixed, always perpendicular to the plane. In 3D, it becomes a general vector and can point anywhere. Therefore, we can represent the rotation state using a matrix or a quaternion. We will use quaternions because of their known advantages: resilience to gimbal locks, smooth interpolation, and efficiency. The angular velocity used to be a scalar number and will be promoted to a 3D vector. It points along the axis of rotation, and its magnitude is the speed. This is the 3D version of positive is counterclockwise and negative is clockwise. The tangential velocity was the radius times the angular velocity. We now do a cross product between the radius vector and the angular velocity vector. This gives us the correct tangential direction at each point. Same thing with the acceleration. Next up we have torque, which is a scalar in 2D and a vector in 3D, and we calculate it as a cross product as follows. The moment of inertia is probably the most interesting concept when moving to 3D. The way that the body resists rotation depends on the axis. A scalar number cannot describe this resistance in 3D, nor can a vector, but a matrix can, because it allows us to encode the resistance to rotation on all three axes. The formula that connects torque, moment of inertia, and acceleration is the key to actually calculate the rotation of a rigid body in 3D. Now that we understand the core concepts, we are ready to dive into the implementation, which is what we will do in the next video. Thank you for watching, and I will see you next time.
Holy shit!